Welcome, Phil Winder. It's great to get this chance to talk to you. We've met a couple of times, but now I get the chance to really sit down and learn a few things from you. I would like to introduce Phil Winder. He's the author of the freshly published O'Reilly book called Reinforcement Learning, now in the modern era. I get to hold it up on my tablet instead of having the book with me. We'll talk about that as well. And he's also the founder and CEO of Winder Research Data Consultancy. So a little bit later on, I'd also like to ask you a little bit more about that.
Sure.
But to start with, I would actually really like to understand a little more about reinforcement learning. I'm fairly familiar with the basics of machine learning. I think a lot of people, at least in the IT world, have gotten some familiarity, supervised learning, unsupervised learning. So what exactly is reinforcement learning in this context? Is it similar, different, a subset? Maybe you can give us a little overview.
Yeah, that's a really good place to start. So we can talk a bit more about the technical aspects and what are involved a bit later. But at a really, really high level, I consider reinforcement learning to be a subset of machine learning, but not because of the way it's used, but just because of the techniques that we're using, the modeling that's done, and all the tooling that is used. It's very similar to machine learning. So it's all part of a very similar family. But the principal difference is that in machine learning, you are using data to optimize for a single decision. So we usually have a goal. We're trying to predict whether someone is good for a loan or not, or whether we want to spend lots of money to recommend a particular item to a particular person. But these algorithms are always working on like a one-shot basis. They're trying to make that decision and make it once, and that's the end of it. Reinforcement learning is slightly different in the sense that it's optimizing for sequential decisions, multiple decisions over potentially a long period of time, but not necessarily. But it's the idea of making multiple decisions over multiple time steps in order to end up at an optimal place. So I think it's always best to try and bring in a couple of examples. So going back to the recommendation idea I just mentioned, with a traditional machine learning algorithm, you would attempt to gather lots of data about what people like to click on. And when somebody types something into a search box, for example, or they visit your website, you will recommend a single set of items, and that's it. And you kind of train the algorithms to put the best one-click items at the top of the list. But if you imagine that the recommendations task is for like news recommendations, what you would end up doing is you would end up promoting lots of clickbaity type articles, all the ones with the real clickbaity, click me for free stuff, or 6 reasons to do XYZ. They will always end up at the top of your list because they are kind of click heavy. But once a person clicks on that and is ultimately disappointed by the lewd advertisement that is behind that website, then they're going to be completely put off your platform or your application. Reinforcement learning takes a slightly different approach, and you would define a measure of success. It's not like just whether they click on it. The measure of success could be something like whether that person comes back to our website, or whether that person spends money on our website, and how much they spend on our website, things like that. So over time, it learns to promote content that eventually leads to increased retention and increased long-term spending on the website, and not just this one-shot, very myopic view of the world. So does that make sense?
Yeah, it sounds like it's a bit bigger picture, and it's focused on an objective, like a more definable objective, rather than some quick result or some action or some set of artificial circumstances. So in fact, indeed, if I'm going to deploy machine learning, I have a real goal in mind, and it sounds like this is meant to get you closer to that goal.
Yeah, exactly. And one of the sort of accidental benefits of setting up the problem like this is that in machine learning, you're often using very technical metrics that are not very related to what the business is trying to do. So you're using things like accuracy and F1 score and all these horrible kind of really technical metrics that the business and the people trying to solve the actual business problem don't really understand. And also you're kind of solving for the wrong problem then. You're solving to improve some technical metric, rather than solving the business problem. But in reinforcement learning, because we're operating over these longer timescales and incorporating maybe a more diverse set of information, we can actually use metrics that are directly coupled to the goal that the business is trying to achieve. If it's like retention or total number of users or total amount of profit, whatever business metric you're trying to solve, but it ends up being much more related to the business.
Okay, so how does it go about doing that? Like, what's the method, and how is that different from machine learning? Like, for instance, supervised or unsupervised learning, which, for those not familiar, really simply a supervised learning is you basically show it the right answer. You go, this is the right answer, find out more of these. Unsupervised learning, at least the way I perceive it, is like, just go out there and see what's there and figure out something interesting about it. And so how does reinforcement learning fall in that analogy?
Yeah, so you're right in saying that machine learning, you often present it with a series of the column labels, but it's basically the goal that you're trying to achieve with that particular task. And over time, you're training a model to you're altering some parameters of that model to encourage that decision, that single decision that is being made, and you repeat that process many times, and to sort of gradually make this model slightly more closer to the goal. Reinforcement learning is similar in the sense that we still use models to make decisions, but the major difference is we're not making one single decision anymore. We're making decisions over multiple time steps. So actually, we're actually going around in a feedback loop where you have the model or the algorithm that's actually making a decision, and then it feeds it back to whatever it feeds it back to, say the user. The user takes some action, and then it comes back to the model again, and then it makes another decision, and it goes back to the user, and back and forth, and round and round and round and round. And the goal is not to make a single decision, but actually take that user. If it's I keep saying user, but we're not restricted to actually having users here. We could apply it to any kind of industrial process. But if what we're trying to do is to take that user from where they were to a new place where we want them to be. And it's this feedback loop that kind of defines what reinforcement learning is. And that's why it's actually it's more technically complex to be able to solve these problems, because it's not as simple as just throwing a lot of examples at a model anymore. We need to throw a lot of examples at a model, and also a lot of these kind of sequential decisions as well. So it's kind of another dimension that we need to add to our data sets.
So it kind of sounds, actually, in a way, they say simplicity is very complex, because
technically, yeah.
With all the complexity, and in fact, it's kind of simple in a way. It's learning the way children learn, right? You take an action, there's an outcome, and you earn some kind of reward for that outcome, and based on that, you take another action iteratively until you get closer and closer to the goal. Essentially, is that about right?
Yeah, that's bang on. And we often use children or animals as a very good proxy to describe how, and animals, and or as a proxy to how reinforcement learning works, because that's how we learn, that's how animals learn, that's how humans learn. We're using the reward or the punishment that we observe in life to refine our behavior, and that's exactly what we're doing within reinforcement learning. We're refining the model within the thing that is making the decision to make better decisions in the future. But the crux of it is we're not trying to refine that model to make a better single decision. Like, at a moment in time, like, I could go downstairs and eat a massive bowl of ice cream, and in that moment I would be very happy. It's very rewarding. But actually, if I kept doing that over and over again, there'll be other consequences that I would have to do more running, or something like that. So I kind of weigh up that, and over a longer period of time, that single decision may not be a good one. So we need to learn how to kind of manage that over a longer period of time.
So now, let's say if I'm a perfectionist, my first question in that mindset would be, what would be the advantage of this versus saying, actually, no, this is the right answer. I want you to learn this answer. It sounds like this method, although it may optimize over time, it introduces a bit of uncertainty, or it takes some control out of your hands. and into the system. What's the advantage of that in the long term?
Well, I mean, first off, reinforcement learning doesn't replace machine learning. Machine learning is still very good for those one-shot decision type tasks. The problem is that many industrial problems are not one-shot in nature. They are actually sequential in nature. And you end up trying to sort of force machine learning upon a problem that it doesn't really fit. So we're not saying that machine learning is bad, and in fact, it's great. But reinforcement learning is better suited to these particular type of problems where you do need to optimize for over a longer period of time. So it's not really so it's not right to say that one is better than the other. It's just that is suited for one set of problems, and this is suited for another set of problems.
Okay. So what are some good examples of scenarios, problems, or conditions where reinforcement learning would be better suited?
So I think there's sort of if I was to try and generalize them as much as I could, then I think there's two general forms of problem that are reoccurring in reinforcement learning. And the first one is what we have sort of, badly described already, but it's the idea of optimizing something. It's the idea of attempting to use RL to help problems that last over a long period of time. So like trying to let me try and think of a better example than not reinforcement learning. Like, for example, if you were building a social media platform, for example, and one of your primary metrics is engagement, the amount of people that are coming back to your platform over and over again, then you could make changes to your user interface that could significantly hamper that engagement. If people get pissed off at the UX, then they're not going to come back again. So you could use reinforcement learning to learn over time which UI configuration turned out to be the best for user engagement. Okay, so that's kind of one group of examples where you're trying to optimize something over longer periods of time. The second common use case is when there are problems that have a very complex level of control that can't be hand defined, that can't be manually defined. The classic example is something like robotics. So if you tell, and it's often the simplest examples actually that sound really easy to solve, but are actually incredibly complex. And I keep coming back to the idea of pick and place robots. And the idea here is that you have, imagine two, like a conveyor belt, for example, in a box. And the goal is to pick things off a conveyor belt and put them in the appropriate box so they get shipped to your house. Like instinctively, that sounds like a really simple problem to solve. But actually trying to teach a robot to pick up an object of an arbitrary shape, like this could be made of cloth, plastic, metal, could be a box, could be a sphere, it could be, all sorts of different shapes. And it turns out that it's nearly impossible to be able to program a robot to be able to do all of those tasks. And instead, you need to teach it. You need to allow it to learn how to do that for itself. And so the way in which they do that, they use reinforcement learning to, repeatedly try and pick up things. And it basically learns from first principles how to pick up an object and put it in a box. And that you can't do that with machine learning because it's not just one task. It's like, many thousands of tiny little motor movements that are getting it into that exact, that right position. And it's pretty much impossible to be able to hand program that. So robotics are a great example of that, but there's many other industrial control systems that kind of have a similar set of problems. For example, in like inventory control is one thing that I've recently got interested in, and this is the idea of like, how do we control the stock of items in warehouses? How many do we have? Where do we put them? How do we basically optimize for various different things, whether preventing things going out of stock, improving the organization of the warehouse, so we reduce the amount of time to get frequently bought items and things like that. Again, you could technically attempt to define that statically and try and write all these rules out by hand, but it would definitely be suboptimal, and it's much more efficient to learn these over time.
Yeah, and that's a great example, inventory, because I think almost any business can relate to that. Well, maybe except for the software business. But that's, and that's one of those, in fact, it kind of does lead to another set of questions that, in there's a lot of buzzwords around data, big data, and, what's the running joke? AI is written in PowerPoint, machine learning in Python or something like that. I pull it backwards, but, and I think one of the results of that is that many businesses, many organizations, many people assume that they don't have a valid use case, that well, I'm not making self-driving cars or curing cancer, so that's not for me. But in fact, it sounds like there are actually a lot of applications that even a small business could use, or somebody that doesn't have a lot of data. How does one get started in this when they don't have a whole lot of data to work with?
Yeah, that's a really good question, and I think actually the clue is in the question. The problem is not it's never a lack of data. It's the most common problem is not seeing that there's a problem in the first place. It's defining the problem that you're trying to improve or trying to solve. It's one of the hardest things to do, because unless you can just see a replica example, a copy paste equivalent, it's actually incredibly difficult to spot where you can apply these techniques and apply these methodologies. And in fact, it's not something that's taught that much, to be honest. I feel like when I sort of teach so I have this idea in this chat this talk that I give, where I say that software, ML and RL are kind of are automating different parts of the business. So at the bottom level, you've got software engineering, which is automating sort of basic business processes. So it's things like how to connect to your printer, send an email to this person when they purchase something, things like that. That's automating a process. Machine learning is automating the decisions, is these one-shot decisions which occur in businesses, like should we accept this price, yes or no, things like that. And then at the top level, you've got strategic level business practices, which are defining things that happen over time. And it could be something as innocuous as C-level strategy, where you're defining where your business is trying to what your business is trying to do. And you could use something like reinforcement learning to kind of optimize your strategy and your direction for your business. So I think thinking of it in that kind of triangle, that sort of pyramid stack. So even at the software engineering level at the bottom, there's many things, many processes that you do every day that you maybe could consider you could consider automating. You could consider bringing in software engineering in order to automate those processes. And I think that because you can kind of visualize and enact those processes quite simply, it's relatively straightforward to be able to define how software can help you.
Yeah.
Take it up a level. And again, if you're thinking about the decisions that you're making on a daily basis, then it becomes a little bit more tricky, because decisions are often not written down. They kind of happen as a part of your job without you even thinking about it. Before we started this call today, you decided to set up the recording on this screen and that screen just because your past experience told you that things fail. We could probably automate that decision. The risk of Zoom not working or something. We could build a model to predict that, but actually actively thinking and deciding to do that is actually quite a difficult thing to do, because it takes some level of stepping out of your you kind of need to view what you're doing from an outside perspective. And then there's RL, which is the same thing again, but it's not just single decisions, actually over a long period of time. So what are you doing on a daily basis that is trying to get you from where you are now to somewhere in the future? And trying to spot those problems is incredibly difficult. So I think, that was quite a long-winded way of describing that. Actually spotting strategies and choosing which strategies are the best to improve and optimize is a very difficult thing, and it's at the problem level. That's where most of the problem lies. It's not the data, it's not the tooling, it's not the technology. It's the problem.
Yeah, it's funny in a way. Again, it is complex, but in a way, it's sort of comes back to being simple again. As I think about like, and recently I talked with a friend who came to me for career advice. Whether or not to take a certain job or whatever. And it's, like you say, it's something I've just kind of done and only in hindsight sort of thought through. I always think anytime I'm considering a job, a project, or anything, I always think to myself, after I leave this job, project, or whatever it is, am I going to be closer or farther from my retirement goal? Like, and whatever that may be. I may even be wrong, but in a way, I guess that's kind of, it all comes back down to this. You give this agent, I guess, a goal, and every step of the way, it's like, well, I don't know if I'm getting there or not, but I think I'm a step closer, or I think I'm a step further. Is that more or less a good way to generalize it?
Yeah, that's a good way to generalize it. And you're also introducing a really key concept there as well. And this is the idea of it's the temporal nature of reinforcement learning. Like machine learning is still it's still tricky to use, but it's a lot more straightforward in that you're using a snapshot of data in time. It's like a fixed snapshot. It cannot change. It's effectively immutable at that point in time when you're looking at it. But with reinforcement learning, the context and the data is constantly changing. It's constantly evolving, and you need to be very careful when you're choosing these problems. That, like you said, you need to actually experience. You need to make these decisions and experience the effects of these decisions before you can actually learn from them. And so when you're giving career advice, it's a really difficult thing to do, because it takes many, many, many years for the effects of your decision that happened years ago to actually come to fruition. And reinforcement learning absolutely requires that feedback in order to learn. So you need to try and focus on problems that provides as a rapid amount, the fastest amount of feedback possible, so that the algorithm learns quicker. Because it's all great, like we could build an RL algorithm to optimize future earnings or something, but it's over such a long period of time that's kind of an intractable problem almost.
Yeah, it's like what we try to do intuitively and often don't do so great at. Maybe I need
to
guide my career, actually. So that's great. So now, at the risk of going slightly more technical, and this is probably about the limit of what I'm capable of getting into, but as I was kind of browsing through their book, I learned about something called the Markov decision process, which, as I generalize it, or as I've kind of internalized it, it sounds like what it is you the agent, whether it's a software model or whether, in life it's you as a person, makes part of the decisions, and random chance makes the other part of the decisions. What's the advantage of that? In a practical sense, you mentioned, I think it was in a context of an A/B test in a website, but in general, what's the advantage of introducing that randomness to the decision process?
So the key, well, let's step back a little bit, because people might not have heard of the MDP first. A Markov decision process is the formalism, it's the mathematical definition of reinforcement learning. So effectively, this is the framework that you use to build your problems around. So you decide your problem, what your problem is, and then you fit it around an MDP. And as long as it fits into the mathematical definition of what an MDP is, then it can be solved by reinforcement learning. So think of it as a framework. It's got several components in it. One of those is called the agent, and you're exactly right. That is the thing that is actually making the decisions. It's the piece of software. It's the child learning to ride the bike. That's the thing that's actually making the decisions. Once they've made a decision, that decision gets fed into something called an environment, and the environment is everything else that is not the agent. So if you're learning to ride a bike, then the environment is the outside. It's the real world. It's the things you can see, the wind that you can feel. It's the pain when you fall off the bike. And then that environment gives you a set of observations. It gives you a view of what's going on in that environment back to the agent. And it's not necessarily complete. It could be hidden in some way. So for example, if you're riding your bike on the road, for example, your view, your observation doesn't consist of all of the cars behind you, because generally you're not looking behind you, you're looking in front of you. So it's only partially observable. But anyway, it is a representation of the environment. And also what comes back from the environment is this feedback mechanism, is this thing that tells you whether you have achieved what you're trying to achieve or not. And that could be like, if you're falling off your bike, it's a negative reward. If you're, going the fastest you've ever been and it's very exciting, then that's a positive reward. And the same thing happens in business as well. So, for example, if a person purchases something, then the amount of cash that they've spent is the reward. You've gained that much profit. And design and basically, part of the art is taking your problem and designing the MDP to suit your problem. Catching up to the last part of your question, there is, you asked about who actually makes the decisions. So it's the agent that actually makes the decisions, and you're talking about, you mentioned this random choice here. So you don't need to choose random. The whole purpose of the random part is to encourage exploration. Because especially when you start out, like imagine a child learning to ride a bike the first time, like they don't even know what pedals do or what handlebars do. So they need to actively experiment in order to figure out what they do. Eventually they'll learn when they push down with their legs, the pedals will go forward. And that's an important thing that they will then learn and incorporate into their mental model. For next time, they then know that they need to push down to go forward. Interestingly, like if you go to Amsterdam, so if people watching here haven't been to Amsterdam, the Dutch are very fond of bikes that have hub brakes. And what that means is that you actively need to pedal backwards in order to brake. So not even the first time, pretty much every time that I go to Amsterdam and ride a bike, I instinctively jump on my brakes and then realize I've got no brakes, they're not there. So I'm actively having to experiment like how to slow myself down. And so that's what the random elements within particular agents are trying to do. But that is the kind of it's obviously not the best way of doing this exploration. It's entirely random. So there's lots of other mechanisms that are a bit more directed, a bit more intelligent, that are actively sort of trying to search for new and interesting things, but in a more intelligent way. It's just random is one of the simplest ways of doing that.
Yeah, I love the Amsterdam example because I happen to be in Amsterdam, and actually I have the opposite. When I go somewhere else, I go backwards and nothing happens.
Nightmare.
Of course, you're in the UK, so the other one is when I go to the UK and get into a car, I have to suddenly
exactly.
It's the other way around. So.
Yeah.
No, that's great. No, that's really it's fascinating, and it sounds like, I mean, the first obvious thing I think of is like autonomous vehicles. They must use quite a bit of this, in their development, for safety and other issues and things like that. So it sounds like there's really a lot of use cases. In fact, it even sounds like probably what someone like me thinks is just machine learning might in fact be reinforcement learning.
Potentially.
It covers, it sounds like. So now, just thinking in the greater topic of data and analytics, there's another little section that you wrote about, which I also found interesting, which was all about ethics and safety, safety, security, ethics. This isn't specific to reinforcement learning, but it's certainly relevant. The more data is out there, the more we kind of hand over to autonomy or autonomous things, or automation, I should say. The more risks there are, the more security threat we create. What is your stance about ethics, and how do you manage that with something like reinforcement learning or just machine learning in general?
Well, that's a really massive question. I mean, in 3 words. So I mean, ethics as a subject is a massive subject. I'm just about to read a new book. I've forgotten her name now, but there's a lady. It's another O'Reilly book. A lady has just written it, and it's about the ethics of machine learning, and it has some sort of practical tips on how to do this technically. I think largely though, ethics is a much bigger than the engineering industry. It's it should be involved like throughout public life, a government level, a local level, like. But I mean, the more we use technology, the more we learn about it, and the more dependent we become on it. And yeah, I'm not entirely sure I'm going with this, to be honest. I think like it's a really hard question to solve.
Yeah, absolutely. I mean, I think, in a way, it's kind of like we've invented fire, and of course, as we all know, fire
Yeah.
can be used for good or for evil. It's fire itself is not evil; it's just how you use it, right? You can cook your food, or you can burn down someone's house, And we've come to a place where we've kind of got that under control as a society, and I guess we need to get there with data.
Yeah, but it's very different in the sense that like when you're using fire, like you can probably hurt yourself, but it's unlikely to hurt other people. But when we're building things like the software that we're building, like it's very unlikely to hurt you, but it's quite likely to hurt somebody else. So it takes an incredible amount of distance to be able to actually ask the question, is what I'm doing right now, is that going to affect anybody? Because like most of the time, 99.9% of the time, you just don't even think about it. It's not like that you're not a moral person, or you don't have ethics or something. It's just you don't even think about what you're doing. It could be taken that way. So I think like the first thing that we can maybe do is just as individuals just consider it a little bit more. I've often heard that engineering is like not a regulated, or not a fully regulated industry. So like people who practice medicine, they have to take the Hippocratic Oath, and they have like legal obligations to basically do good and not bad. Like that doesn't exist in engineering. And I've heard of many people sort of talk about the idea of implementing something like this, but I feel like that's not really the right approach either. But there needs to be some sort of something in that direction, some common agreement about the things that are right and the things that are wrong. And in fact, that's what governments are for. That's what laws are for. That's what regulations are for. So maybe the answer is just let the politicians and the lawyers do their jobs, and we'll be all right in the end.
Yeah, it is definitely the mark of a new kind of emerging power in an industry. Like I think 20, 25 years ago, you could talk about the finance industry, the pharmaceutical industry.
Right. Yeah.
The tech industry was still this kind of cute, nerdy, thing on the side that makes their TVs better. And I think in the last 15 years, especially 10, 15 years, it's really started to take a whole new role in society. And
yeah, exactly.
Really cool to start thinking about those things. I agree.
Yeah.
So, well, that's, like I said, we won't solve it. Well, I didn't say that, but we certainly weren't going to solve it in a few minutes. It's an important topic to touch on, I think.
Yeah, so you did mention safety though as well, and that is a little bit more tangible and a bit more solvable. And reinforcement learning in particular sort of attempts to tackle that head on. There are for certain tasks, it's really important to sort of mathematically prove that if we apply a constraint, if we say that you cannot go outside of these bounds, that you can prove that the algorithm that is derived from that reinforcement learning algorithm also conforms to those constraints. And so there are algorithms that exist out there that are provably safe. The problem with them is that they often add so many constraints that actually it makes the problem harder to solve. So a lot of other frameworks that have been suggested kind of sit on the outside of the model and effectively act a bit like a watchdog. They kind of watch to see what is happening, and if something is ever about to be unsafe, then it's just like just chops off the action, so it can't be unsafe. So they're kind of generally the two approaches that researchers have taken to apply safety constraints. But it's eminently doable. Yep.
That's very fascinating. Actually, I remember when maybe a few years ago when they were talking about training autonomous vehicles here in Amsterdam. And the first thing I thought of were just dozens of bikers getting knocked into canals and things like that. And ultimately, I actually don't know if they ever did that testing, but ultimately this would be a very a clear example of that. Since if you have been in Amsterdam, you can under normal times. You see that there doesn't even seem to be any rhyme or reason to the bikes. There's no order. They just fill in the space like liquid. So, it's probably an especially challenging problem for machine learning and other types of data science. So.
Yeah, definitely. And you can only be provably correct if you have the like correct data in the first place. Like part of the problem and part of the reason why the sort of the provably safe algorithms don't work particularly well is because it's impossible to kind of attain the level of detail in the data that is required to be safe in the first place.
Yeah.
So there has to be a compromise somewhere, and not sure where I'm going with that. It's a hard problem. Of course,
unknown unknowns in that problem.
Exactly. Yeah.
Exactly. So, coming back onto the business angle of it, how would you describe the opportunity cost of not doing something with data? I've run into lots of businesses that don't take on these data projects, or they try to, but they don't get started, or they get a lower priority. We could probably come up with examples in every sector, but in general, if you don't do something with data science in your business, what is the opportunity cost in the coming years?
Yeah, so it comes from there's a range of sources really. So the first one, and usually the primary driver actually, is that others will do this, and so if you don't do it, they will have a competitive advantage, whatever that may be. Maybe it's from a purely marketing angle. Maybe it's a functional thing. Maybe it's a process or just like an internal management style thing, and it makes them more efficient. But whatever way it is, other people will take advantage of this, and they will reap the benefits of doing that. The hard part here is that it's kind of like the inverse problem of deciding which problem to solve first. It's like evaluating whether the problem that they're solving is actually that important to your business. And quite often you might see people do things and it may be in a similar sector, but they're doing something completely different. So it's not really relevant to you. But in other cases, you might find that that people in other industries are branching out to other sectors, to other industries with their technology that become a competitor when they weren't a competitor before. And there's lots of really big companies that are very good at doing that. So that's really hard to that's a hard problem to solve in itself. So anyway, opportunity cost number one is competitors taking advantage of the data and you don't. Number two is that the loss of efficiency that you could have in your business. Like if you imagine that you're spending most of your time enacting some process or enacting some decision or enacting some strategy, you could be spending that time doing something else. So if you don't automate that, you're wasting time, you're wasting your time and your company's time. Whereas if you do automate that, you'll have more time to do other things. It's kind of the classic automation requirement. And then I think maybe the third one is we've covered competitors competing, internal efficiency, and the third one is opening up new markets, I think, or opening up new products and new ways of doing things that ultimately open new markets and new revenue streams for you. Many traditional businesses have an incredible amount of domain knowledge and domain expertise that can be exploited in a more modern way. And as part of doing that, data may be part of that. It might be a pure software play, it might be a pure machine learning play, or it might even be reinforcement learning, who knows. But you can probably leverage some of that institutional experience in order to open up new revenue streams. I think that's really what I'm trying to say.
Basically, if you're sitting on this kind of value, you have to put it to use. Otherwise, it doesn't do anybody any good, right?
Exactly. Yeah.
And the good news, of course, is that we have, of course, Winder Research, which is the company that you founded and that you are leading, you're founder and CEO, which is a consultancy for just these types of problems, not just reinforcement learning, but all kinds of machine learning. What are some of the projects you work on? There's a few interesting projects that you've done that might apply more widely.
So we tend to work on quite a diverse range of projects. Traditionally, we have focused more on the data side of things, the pure data angle, where companies are attempting to, they typically have or are aware that they have large amounts of data and they can do useful things with them. And we help them analyze and automate and build off applications based upon that data. But actually, more recently, we found that many companies have either already done that or are doing that themselves. And actually, they're struggling with the process of doing that. Like, actually, how do we take our data and how do we build our machine learning platforms and applications? And that's actually the problem they've been struggling with. So we've also been working a lot to help companies build out their ML platforms, their ML processes. And ultimately, we're trying to make it easier for them to develop their ML and RL applications. So that's generally the sort of the two themes of the business. One is the pure data side, where we're helping them on the data science front, and the other side is like the engineering side, where we're actually helping build the systems to build the products. So to give you a couple of examples of that, I won't mention any names if that's okay, because it's kind of a public recording. But there's several companies that tend to be smaller in size, where we've helped them build out a significant part of their product from the data that they have from their customers. One of the coolest applications was a machine learning based web application firewall. So the idea here is that you have a firewall that sits in front of your applications, which attempts to block people, attempts to block access whenever they're trying to do something a bit naughty. And so we helped them build a product that allowed the firewall to kind of learn over time from attempted hack attempts to block certain patterns, certain features within the data that are that look like hacking. Okay, so that was pretty cool. It's a pure sort of data-driven product there. On the other side, on the engineering side, we work with larger enterprises typically to help them build out their internal platforms and processes. So here we're building things like data science platforms to help their data scientists use their data and do their data science in a more efficient way, and ultimately actually build out products and solutions from their efforts. So helping them build their data science applications there. Sometimes it's dedicated platforms. We worked with one client to build a dedicated NLP platform, natural language processing platform, that allowed them to build up and wire up new NLP applications from some sort of base primitive techniques that we helped provide. So that's kind of a flavor of some of the things that we work on.
Yeah, I mean, it's great. It's one of the reasons, I guess, that, people like you and myself are employed, is that, of course, these companies have data, they have technology, but it isn't their core business. If they're a bank, money's their core business. If they're an energy company, energy is the core business. And yet they have all this stuff of value. And so then this is where I think you guys are bringing really a lot of value to bring you in to help them along with that part of it, so they don't suffer from the opportunity cost ultimately.
Yeah, exactly. Yeah, and I think also actually the majority of people I speak to, they would kind of love to do some of this themselves, or they would like to task their employees to do it for them, but they just don't have the time. They're concentrating on the core business, they're concentrating on making it better for their customers, but they kind of know that they're missing out by not doing this. So quite often we come in and we help them do sometimes quite research driven projects to just provide them with the ability to say yes or no. It's like, yes, this is definitely an approach we want to invest in the future, and they wouldn't be able to do that without people like us.
Yeah, no, it's great. So this is starting to become my standard closing question. Obviously, the name, I'm from Cloud Native X, and of course, we were talking about buzzwords earlier. Big data. In a way, this word cloud native has become a bit of a buzzword. It's meant different things at different times to different people. How do you see that term? What does cloud native actually mean when you say it?
Well, when I say it, I'm usually using it in the context of doing an ML or data science. So I often say that we're a cloud native data science consultancy, not just a data science consultancy, because for me in particular, the word data science and ML, it doesn't kind of imply any application. It doesn't imply a product. It doesn't imply kind of engineering that comes out of that. And of course, like statistics, maths, pure data science, the These are all really important subjects that still need to be done, but in and of itself, they don't usually end up as being actual products and actual things you can use. They're typically just reports. So we tend to specialize more in the development of usable software and usable products. And that typically involves a lot of software engineering, a lot of cloud engineering, and a lot of cloud native technologies, which again, I think of as being it's more of a way of working than a particular set of technologies, but it's this idea of being cloud first, and scalable first and repeatable first, rather than being rather than the alternative.
Yeah, basically, kind of one of the definitions I've heard is sort of untethering the environment, the data, the technology from some physical anchor, like a server in a room with air conditioning, focusing back on the part that matters, basically. So, no, it's great. No, I really, really appreciate it. I'm hoping we'll have many more interesting conversations like this. This is a great introduction. So just to mention again, reinforcement learning. I got this from Amazon.com in the US because apparently, if you have a US based credit card, you can't get it somewhere else, but it's very easy to obtain. And O'Reilly is, basically my whole career, I almost, at least half of it, I have to owe to O'Reilly books. So I think it's so thanks very much, Phil. It's been fascinating. And we hope to hear very much more from you in the future, and look forward to speaking.
No worries. Thanks, Lee. Thanks for having me.